Alright, y'all. So in this video, we're going to look at a problem about a ski lift. The ski lift has some skiers that are going to be taken up to the top of the hill. And the question eventually we get to, you can pause and read through it if you need to, but the question being asked is, what is the average power that the motor has to supply? Alright? Now, to start with that, I think it's probably a good idea to think about power. Well, what exactly is power? In order to be able to solve for it, we need an equation that has power in it. So if we start with that, we know that power is equal to the change in energy over the time, or the change in time, depending on how your equation looks. So really, in order to be able to figure out the power, I need to find out the change in energy of some object and the amount of time that it takes to do that. And so as I'm looking through the problem, I see that a single rider is being lifted up this hill, up to the top. Now, if you've ever been on a ski lift, the thing with the ski lift is that it moves with a constant speed all the way up. Now, what that means is that my kinetic energy is going to be the same at the beginning and the end. So I'm not going to have any change in kinetic energy, but I do see that I'm going to have a change in height, right? The change in height is going to lead to a change in gravitational potential energy. Now, of course, at this point down here, I can define my height to be 0, which means I got 0 energy there. So all I really need is I need to find out when that skier, that 70 kilogram skier, goes from down here to up there, how much gravitational potential energy did they gain? So we go gravitational potential energy is equal to mgh. We do know the mass. The mass of that single person is 70. And you may say, well, what about all that other stuff? What about others? Don't worry about those other numbers. They might not be important. Maybe they will. We'll figure it out as we go. Right now, I know I need power. Power is going to come from energy over time. The change in energy is going to depend on the gravitational potential energy that's increasing. All those other things, we'll pick them up as we need them, right? As long as I have direction, I'm going to go with that direction until I run out of things to do. If I run out of things to do, then maybe I'll look at those other points and I'll see how those things connect to the question that I'm looking at. So I've got my mass, I've got G, which is 9.8, and I don't have the height. So this is where I'm going to say, okay, well, now maybe I need to go back to my drawing. I need to see if figure out if I can use that other information to figure out what the height is. So it does tell me that the skiers go up a 600-meter slope. And so from here up to there is 600 meters. And it does give me the incline of the slope, which is 30 degrees. Now, hopefully you're recognizing that that's really nice, because now I've got the length of my hypotenuse here, and I've got the angle there, and the height, of course, is always perpendicular to the ground, which means I got a right triangle. And you can figure that out. You can use your calculator if you want. You can say, oh, this is a 60, 30, 90 triangle. I learned about that in geometry class. You can solve this however you want. But eventually, you should be able to do the calculation and recognize that the height then is going to be 300 meters. Again, I invite you to figure that out however you want. Don't just take my word for it. Do it on the calculator. Think through your triangles. Use your trig, right? You could do opposite over hypotenuse. That would be sine of 30 equals opposite over hypotenuse. Do that however you would like, but we're going to end up getting 300 meters. So that's then going to go in for my height. And then I should be able to use that to calculate the gravitational potential energy at that maximum height. And so I go 70. First I'm going to turn my calculator on. I go 70 times 9.8 and then times 300. And I get that a single person that has a mass of 70 kilograms will gain 205,800 joules of gravitational potential energy, as long as we're talking about the person-Earth system, of course, which is what we need in order to be able to look at gravitational potential energy. All right, so if he started at the ground, which was 0, and now they're at this, so this is the change in energy. So I can go ahead and I can put this into the change in energy there. Now I need the time, and it does tell me, let's see, to lift this, under maximum conditions, 6 riders per minute arrive at the top. Okay, Well, if this is the change in energy for one person, I don't have the time for one person, but I have the time for 6 people. So why don't we take this energy and say, you know what, let's multiply that by 6 to get the energy of 6 people, starting at the bottom and moving up to the top. And so I'm going to take that, I'm going to go times 6, and I get that the change in gravitational potential energy of 6 people is 1,234,800 joules. Now, because I did 6 people, I know that it takes 6 people 1 minute to get to the top. So now I have a change in energy and I have a time. So instead of using this, I'm going to use this for my change in energy. So we're going to be able to go power equals the change in energy of 6 people divided by the time for 6 people, which is 1 minute, but I like it to be in SI units. So I'm going to go divided by 60 seconds. So I go divided by 60, and I get that the power is 20,580 watts. All right? 20,580 watts, joules per second. Now, that's the power necessary to get them up the hill. Now, this is the last piece, because remember the question is asking about how much power the motor has to supply. But unfortunately, 60% of the energy supplied by the motor goes into friction, right? There's all these moving parts, the track's moving, going on, the gears, all these things. You're losing a lot of energy due to friction. And so we're actually going to have to now take one more step. We're going to have to say, well, I get a certain amount of power from the motor, right? So the power that the motor supplies, 60% of that is lost due to friction. So this is the power supplied. I'm going to lose 60% of that. So that would be 0.6 times whatever power is supplied. Right? So the total power minus 60% of that power, and then that will equal the power that I actually get. Okay? Now that was this number. That's what I actually get out of it. That's what actually happens, is those people moving up. So I've got this number, and then you'll notice that these two are like terms. Because these two are like terms, I can subtract them. So I can go 1 power supplied minus 0.6 power supplied, and I get 0.4 power supplied equals the actual power that I get, which is 20,580. Now you can solve. Just divide that number by 0.4, and we get that the total power supplied by the motor is equal to 5,1,450 watts. And there we go. We've managed to answer the question. Now notice that this time we didn't have to worry about kinematics or forces or anything like that, because the question was directly asking about power. That right there gave us enough to know I need to go straight to power. When I looked at power, I recognized, well, power comes from energy and time, so therefore I'm going to need to find the energy, which I did, the change in energy of one person, which I was able to use once I recognized that I only had time for 6 people, and so I used the energy for 6 people and the time for those 6 people to help me get the total power that I needed to get them to the top. Once I got them to the top, I then could use that information with the information that 60% was being lost due to friction, and I was then able to find the total power that actually has to be supplied by the engine. Now recognize that I do only have 2 significant figures here, and so the 6 riders, that is not one significant figure, because I know that there's exactly 6 riders. I'm not going to have 6.1 riders. It's exactly 6 riders. So that's not one sig fig, that's 2. The other ones, 60%, 30, 60, notice I have the decimals there. I apologize, I should have had a decimal here and a decimal there to be consistent. 2 sig figs. So my final answer, I'm going to go ahead and just write 51,000 newtons will be my answer in the number of significant figures. So hopefully that was helpful, made sense, and let me know if you have any questions. See you next time.